For about the last 50 years, there's been one element that has quietly powered our entire world, and that's silicon. It's literally the foundation of the information age. But the future we're all building, the one with artificial intelligence, 6G, electric vehicles, it demands more. It needs a whole new class of materials. So to really understand what they are, let's meet the key players in our story. To really get this shift, think about it like this. On one side, you've got silicon. It's like the diligent, hardworking student. Super reliable, cheap, great at all the general-purpose stuff. But on the other side, we have compound semiconductors. Now, these are the genius specialists. They're the ones you call in when you need a very specific, extraordinary ability. We're talking superpowers, like incredible speed, the magic of creating light, and the raw strength to handle immense power.
So first up, we need to understand why the king is suddenly being challenged. Let's dive into Section 1, Silicon's Hidden Limits.
What I love about this slide is how it visually frames the whole story. Look on the left. You see silicon's really rigid atomic structure. And that structure, it creates some serious physical limits. It dictates how fast its electrons can move, how much power it can handle, and it makes it, well, pretty terrible at emitting light. But then, look to the right. You see our compound semiconductors just smashing right through those boundaries. They have these amazing properties, like a wide band gap and high electron mobility that just leaves silicon in the dust.
And this isn't just some abstract, theoretical problem. The demands from AI, from next-gen wireless, from the green energy revolution, they're creating a perfect storm of requirements that silicon, on its own, is just not equipped to handle. The need for a specialist has never, ever been greater. So let's explore the first of these incredible superpowers. Section 2, a need for speed.
This image here just brilliantly illustrates what we mean by speed. So inside a silicon chip, electrons are moving through this atomic lattice, kind of like cars trying to get through a congested city street. There's a ton of resistance. But in compound semiconductors, something like gallium arsenide, the path is wide open. It's a superhighway. It lets electrons move many, many times faster. And that property? It's called high electron mobility.
Okay, so the big question is, why does that speed actually matter? Well, it's the engine behind our entire connected world. That lightning-fast data transfer and low latency you need for 5G, and what we'll need for 6G, or the high-frequency signals for satellite communications, and the incredible precision of modern radar systems, all of it depends on this electronic superhighway.
All right, next up is a superpower that honestly feels a little bit like magic. Section 3, the magic of light.
To make this concept really, really simple, just imagine this. When an electron inside of silicon tries to release its energy, it's like this big, clunky golem. It struggles, it's inefficient, and it wastes most of that energy as heat. But in a compound semiconductor, that exact same process is like a graceful fairy, effortlessly converting that energy directly into a photon, a tiny particle of light.
Okay, so that was the fairy tale version. Here's what's actually going on. Silicon has what physicists call an indirect band gap. That just means electrons can't drop down and release energy as light very efficiently. It's a clumsy process. Compound semiconductors, on the other hand, have a direct band gap. Electrons can drop straight down, releasing their energy perfectly as a photon. The difference, really, is night and day. And this one single property is the reason we have modern LEDs and lasers. It's the tech that powers the 3D sensing in your phone for stuff like Face ID, and it's the literal eyes for self-driving cars through LiDAR sensors. So yeah, this isn't just magic, it's absolutely essential technology.
All right, let's look at the third and, maybe the most critical superpower for our energy future. Section 4, Masters of Power.
Let's meet the knights of the semiconductor world. Silicon carbide, or SiC, and gallium nitride, GaN. Think of them as warriors who are facing down the dragons of high voltage and extreme heat. Their armor is something called a wide band gap, and it's basically a shield that allows them to withstand conditions that would just completely melt poor old silicon. And here's what that suit of armor looks like in technical terms. That wide band gap means they can handle way higher voltages without breaking down, and they can operate efficiently at much, much higher temperatures. So while a traditional silicon chip is overheating and failing, SiC and GaN just keep on running, cool and efficient. So what does all this superior strength mean for us? Well, it means they're absolutely essential for making our energy use more efficient. You could say they're the backbone of the entire green energy transition. And look, this is not some far-off future tech.
It's happening right now. In electric vehicles, these chips mean faster charging and longer range, all because they reduce energy loss. In solar farms, they convert energy more efficiently. And in giant data centers, they manage power so much more reliably, cutting down on a massive amount of electricity waste.
So, we've seen speed, light, and power. But, there's one more trick up their sleeve. Let's bring it all together in our final section. Section 5. The future is compounded.
So here's the bonus power: customization. See, silicon is just one element. Its properties are fixed. That's it. But compound semiconductors are made by combining two or more elements from the periodic table. And by changing the recipe, adjusting the ratio of gallium to arsenic, for example, engineers can literally tune the material's properties perfectly for a specific job, whether that's emitting a specific color of light or operating at an exact communication frequency. It's incredible.
So here's the most important takeaway. These specialists are doing way more than just patching the weaknesses of silicon. They are enabling entirely new possibilities. The massive processing power we need for AI, the crazy fast connectivity of 6G, the efficiency of EVs, the resilience needed for aerospace, all of it is being built on this new foundation. And when future industries demand performance at the absolute bleeding edge of what's possible, there is simply no other choice. They are, as the source material puts it, the only alternative for extreme performance.
Look, it took a diligent, reliable, all-rounder like silicon to build the world we have today. But it's going to take an army of these genius specialists to build the world of tomorrow. And that leaves us with a really interesting question, doesn't it? What are we going to call the new age they create?